We're on to section 2 here, and we've got hot tea being poured into a cup. The temperature is modelled by this T equals 25 plus 70, 1.5 to the negative 0.4 T, where capital T is the temperature and T is the time after it was poured. What's the temperature when little t equals 4? So little t equals 4. Big T is going to be 25 plus 70, 1.5, negative 0.4 times 4. Put that in my calculator. 61.59 degrees, and that's to 2 decimal places. At what rate is the tea cooling after 4 minutes? So this is the type of scenario where we're doing a dt over dt. Now we need to find the derivative of, so that's a capital T on top, not a lowercase t. Now the issue here is that rather than having a base E here, we've got a base of 1.5, which means I cannot just go and say my normal derivative and just bring this 0.4 out the front. I've actually got to go and include a log with that as well. So I can do what I would normally do and say it's negative 0.4 multiplied by 70, 1.5 to the negative 0.4 t. But then because this base is not E, what I need to do is multiply it by the log of the base that it is, which is 1.5. Okay, now of course what I can also do here is I can replace that t with 4, because that's what we're asked to find. Now within this here, there is a the scenario where I can use the k, my rate of growth, or in this case the rate of decay here, because the T is getting cooler, and use a KP. Now that's really my my temperature at the point in time, if you have a look at the line here. But I've also got to factor in this 25 that was there. It's really not worth trying to do that with this type of question. If you're an Extension 1 student, you might be looking at that and saying, yeah, that's just a Newton's law of cooling. Yeah, it is, but it's going to be messier, particularly because I've got this log 1.5 sitting at the back. Honestly, it's just easy to go to your calculator here. Now I do go to my calculator, and what I find is that I get that this value is equal to negative 5.934, which means that T is cooling at approximately 5.93 degrees Celsius per minute at that point in time. Now, how long after the tea poured will it take for it to reach 55 degrees? Well, now I know that capital T equals 55. So I'm going to therefore go and say that 55 is equal to 25 plus 70, 1.5 to the negative 0.4 t. This time I'm trying to find that lowercase t. I'm going to take away 25 first and have 70, 1.5, negative 0.4 t is equal to 30, and divide by 70 now to get 1.5 to the negative 0.4 t is equal to 3 over 7. I'm going to have to use a change of base here because I don't have a base that I can naturally use. So I'm going to say negative 0.4 t is equal to the natural log of 3 over 7 divided by the natural log of 1.5. Now there's possibly a little bit of neatening I could do in there, but I'm just going to be going to my calculator anyway, and I'm going to divide all of that by negative 0.4 to find my time to deal with this coefficient there. Now I throw all that in my calculator, and what I'm going to get is T equals 5.22 minutes. And again, that's to 2 decimal places. You could go minutes and seconds there if you would like as well, but 5.22 is what was in the HSC solutions and is absolutely fine. The key thing with this question, I think getting it right, is to recognize that you cannot treat it like a base E question, because it's not a base E question. That base of 1.5 means that we have to respond differently to it. We can't just treat it like a base E question. We do need to include this ln in a couple of steps here, and it means we do have to also do a change of base at the bottom, not just rewrite it in logarithmic form. All right, we've got a question that stumped a few people in this HSC exam. Now, we were told that we've got this regular sided decagon's 10-sided shape with all sides equal. It's got a perimeter of 80, which means that I'm going to straight away say that this length AB is 0.8 centimeters. Is going to be 8 centimeters. I apologize, not 0.8. Because we're just taking that whole perimeter and dividing it by 10. I'm going to say that angle AOB is going to be equal to 360 over 10, which is 36 degrees. Now, the other way I could say that is it's going to be equal to pi over 5 radians. If I want to go and take 360 degrees divided by 10, would give me 2 pi over 10 or pi over 5 radians, which is about 36 degrees anyway. It's about 0.6 radians, maybe 0.7 radians. Now those two pieces of information are going to be key, because what we're going to do is we're going to use this triangle here and find the area of that triangle there to then go find the area of the whole shape, because that area here represents 1/10 of the area of the whole shape. So we're going to find that area and multiply it by 10. Now to do so, what we need to do is we have this isosceles triangle, AOB. Now we need to go find what its area is. Now I don't know everything about it, but I do know that I've got two equal sides. These sides are equal, which means these angles are equal. And then I've got this angle here, 36 degrees. I'm going to treat it in degrees to start with. We're going to avoid the temptation of going radians here, even though it might end up being slightly nicer as a more exact version. But if I've got 36 degrees, it means that these two angles up here, the two dots, or angle OAB and OBA, they're going to be equal to 180 minus 36 over 2, because I take away the 36 degrees from point O there, and then halve it because they are equal, which is going to give me 72 degrees. Okay, so I've now got this triangle that's 72, 72, and 36. So I do need to go find the length of sides OA and OB, because they are also equal. Now to do that, we could go and drop a perpendicular bisector down the middle like that, and then go treat it like a right angle triangle. And we would have a right angle triangle that's got something like this. It would be 18 degrees at the top, because we would halve the 36, but the 72 would remain. And then we don't know anything about this length or this length that we're really interested in, but I do know that this is 4 centimeters. To be able to find the area of my triangle here, I really just need this height. So to go find that height there, I could go tan 72 is equal to h over 4, or h equals 4 tan 72. To find the area of this blue triangle here, I would say area is equal to half multiplied by 4, which is the base, multiplied by the perpendicular height, which is 4 tan 72, which would be 8 tan 72. Now, what I would need to consider is to find the area of triangle AOB, I would multiply that by 2. Now, to find the area of the whole 10-sided shape there, I would then take that number and multiply it by 10. So that means I'm going to be finding 160 tan 72 is my area. Now, throwing that in my calculator, I get it's equal to 492.429. And I could round that to one decimal place, which would be 492.4 centimeters squared, of course being my unit. Now, as I had a look at the solutions just now from Nessa, they get the same number, but they get there very differently. They get there by doing a sine rule for area. Absolutely fine as well. Essentially what they've done is, rather than treating it like a right angled triangle, they've left it as an isosceles triangle, and gone and found the length of OB or AB, or OA, and then done a sine rule on that again to find the area which is absolutely fine. They still get the exact same answer. I just wanted to treat it like a right angle triangle. But go have a look at their solutions if you'd like on their website and see which you prefer. But this is just one option. All right, we've got a continuous random variable. The thing that I would acknowledge here straight away with the continuous random variable is that the sum of my probabilities is going to equal 1, which is what we're going to have to use here in part A. So what I need to do is go between k and 0 for sine x dx, and that's going to be equal to 1. So I'm going to find that primitive. It's going to be cosine x, but now, of course, because I've integrated a sine x, that becomes a negative between k and 0. Now I'm actually going to flip those boundaries there and turn it into between cosine x, so between 0 and k, and substitute those in and have cosine of 0 minus cosine of k is equal to 1. Now it's 1 because the sum of my probabilities has to be equal 1 because the probability density function. Now cosine of 0 is 1. So what that means is I've got 1 minus cosine k equals 1. Well, what that means is cosine k is equal to 0. The first time where cosine equals 0 is pi on 2. So my value for k there is pi on 2, or this probability density function works between 0 and pi on 2. It's also the probability of a trig function, the property of a trig function, by the way. If I go and sketch my cosine function there, is that each of these 1, 2, 3, 4 areas is equal to 1 unit. So each pi on 2, I end up with 1 area unit. So we need to find P of the probability that x is less than 1, giving your answer to 4 decimal places. Now that is not the same as the probability probabilities all adding to 1. What we are finding here is we're going to take our value between 1 and 0 sine x dx and go and substitute those values in. So what that's going to give me is, again, I've got my negative cosine x between 1 and 0. I'm going to switch those boundaries. So it's cosine x between 0 and 1. I substitute those in and I end up with cosine of 0 minus cosine of 1. Now cosine of 0 is 1. Now cosine of 1 is actually not an exact value or a nice value here. So we round that to 4 decimal places. I've got something that ends up looking like this. Cosine of 1, as I said, not a nice value, which is approximately 0.4597 to 4 decimal places. Now what that means is it's about a 46% probability that that's going to happen. Now if I was to draw this as a sketch, I love drawing a graph. If we think about it, this is the part of our probability density function we're working with. We can't do the whole cosine curve because its area adds up to more than 1. It's also negative there. But what we're finding here is, well, this is pi over 2, which is about 1.57. So we're finding out a probability where it's less than about half of that. So really we're finding this area there, okay, where the whole area here is equal to 1. We're finding a little bit less than half of it, which is our probability that we end up landing in 1 or less. That's what a probability density function represents. It's all got to do with the area under that curve. So we're reflecting a circle here. I've got its equation up the top there, and we're going to sketch it reflected in the x-axis. I'm not going to worry about that straight away. I'm just going to factorize it because then I can think about how I reflect it. So I've got x squared minus 6x plus blank plus y squared plus 4y plus blank is equal to 3. I need to consider what my blanks are going to be. I'm going to halve 6 and square it and get 9. I'm going to halve 4 and square it, which gives me 4. Then I'm going to add on 9 and 4 to the right hand side there. So what I get is x minus 3 all squared plus y plus 2 all squared is equal to 4 squared 16. Now, again, this negative means I've got a negative here, whereas this positive means I've got a positive here. Now, if I sketch that circle, this is not the answer, but this is what this circle looks like. This circle has a center at 3, minus 2, okay, and a radius of 4. So it's going up to about there, and down to about there, across to here, and across to there. Once again, this is not the answer. This is what I'm going to take to reflect. That's 3 minus 2. We could go find what those values are, but we are reflecting it in the x-axis. So I'm reflecting in this axis here. So what's going to happen? Well, the x value is actually not going to change. This center ordinate, this minus 2, is actually going to come up here to 2. And so the circle that I need to sketch for my solution, once again, to be very clear, blue is the solution here. It's going to have its center at 3 plus 2. It's going to have a radius of 4, so it's going to go as high up here as 3, 6, go as low as 3 minus 2, and it's going to go as far right as 7, 2, minus 1, 2, and probably not a terrible decision to draw a better circle than I have been able to there, at least just a little bit more neatly and accurately. But what you can see with mine is that I do have those up, down, left, right extreme values. Now, what we really needed to, in fact, in looking at Nessa solutions, they're not too interested in these points here. They just want to see that you have got the center right. So labeling the center would probably be a good idea as well. 3, 2. The key steps here, first of all, I'm factorizing it. Factorize is my first step. Next is to say, well, what's changing? It's being reflected in the x-axis, but x isn't actually changing. It's y that's changing there. The radius also not changing, and then drawing that reflection there as it's done in blue. All right, we've got a max-min problem here. We've got a garden bed that's made up of a rectangle and a quadrant, a quarter circle here. And we've got 36 square meters to use of space, and we want to have a perimeter which is as small as possible. So a max-min problem here. Now we're asked to show that P equals 2x plus 72 over x. As I look at this, so my perimeter here, well, I've got, if I walk around the outside, I've got 1, 2, 3, 4, 5 lengths to consider. So starting from where I was, there's an x plus a y. Now this length here is x, which means that's also x, so another x. I'm going to continue on by saying there's another y as well. Now there's also this quarter of a circle, which would be 2 pi r, which is x, but it's a quarter of that, so it's a quarter of that. Now, so that means my perimeter of this shape is 2x plus 2y plus pi x over 2. Now that's not quite what I've got here, but what I also need to acknowledge is that I've got to write my expressions for area too. So if I said my area of these two shapes is going to be xy plus pi x squared over 2. Okay, well now that's looking a little bit better. And I know that that's also equal to 36. So that should be over 4, not over 2. Over 4. And that's all equal to 36. So now what I can do is start to rearrange this expression a little bit. And I can say that xy is equal to 36 minus pi x squared over 4. And that means y is equal to 36 over x minus pi, minus, not equal to, minus pi x over 4. Okay, so now what I've got to do, I've got to take this piece of information here and substitute it in to there. Okay, so I'm going to replace that y, and we're going to start to get something that hopefully looks a little bit tidier here. Okay, so what's going to happen when I do this substitution? I'm going to get my P perimeter is equal to 2x, that's just the original 2x, plus 2 outside of 36 over x, minus pi x over 4 plus pi x over 2. Now, doubling all that out, I end up with my 2x remains plus 72 over x. Now, that's exactly what we want here. Now, what happens to these third and fourth terms here? I end up with minus 2 pi x on 4, which is pi x on 2, plus pi x on 2. So those two are equal but opposite, like terms, cancel each other out. I'm left with this expression here for p, as I'm asked to find, the p equals 2x plus 72 over x. All right, so now we're going to use this fact here. I've got p equals 2x plus 72 over x, and I'm actually going to rewrite that as 72 x to the minus 1. Now, find the smallest possible perimeter of the garden bed. We're going to do that using the derivative here. Now, I'm going to find dp over dx, which is going to be 2 plus minus 72x to the minus 2. I'm actually going to rewrite that, get rid of that plus there, which means I've got 2 minus 72 over x squared, which is 2x squared minus 72 over x squared. Now what I want to find is where that's equal to 0. dp over dx is equal to 0 because that's going to be my turning point. So I can ignore my numerator, my denominator there, and just solve for my numerator, which is 2 outside of x squared minus 36 equals 0. Now x equals plus or minus 6. Now, of course, x is greater than 0. So that means x equals minus 6 gives me my, my solution there. Now, considering my perimeter here, that means my perimeter is going to be 2 times 6 plus 72 over 6, which is 12 plus 12, which is 24 meters. Now, I do as well want to prove that that is in fact the minimum. And what I'm going to do there is then go and use my next derivative, d squared p over dx squared, which is going to be equal to 144x to the minus 3, or 144 over x cubed. Now, if x is greater than 0, that second derivative is greater than 0 as well. So therefore, it is in fact a minimum, because that's, if I've got a second derivative that's positive, it means I'm concave up, which means I'm going to have a minimum turning point, which means x equals 6. Sorry, I've miswritten this here. That should say plus 6, not minus 6, because x is greater than 0, which means my perimeter is going to be 24. That's the minimum, which happens when x equals 6. We could go find what y is as well, but we're not actually required to do that. What we're asked in this question is find the minimum perimeter, which is exactly what we just did. An annuity question here where we're asked to use a recurrence relation. We've got to find out how much is in this account after the third withdrawal, or the third month in that case. So what's happening is that this $60,000 earns interest and then goes down by $800. Earns interest again, goes down by $800. The $800 is a fixed amount, whereas the interest that it earns is an adjustable amount depending how much is in the account. So each time we take money out, it's going to get less interest essentially. So having at the first one, A1, and we're given this here, and the interesting thing is there's AN minus 1. So A1 is going to be A0, which is 60,000, times 1.005, 0.5%, minus 800. So after the first month, that's going to be equal to a gain of $300 in interest, but a loss of $800 that's been withdrawn. So it's going to be $59,500. Now A2, repeating this pattern, is going to be the new amount that was in there in the previous month, gain the interest, take away 800, which is $58,997.50. Let's do the same thing again. A3 is going to be that amount, 58,997.50 minus 800. Sorry, it gains its interest first, so it goes up by 1.005 or 0.5%, and then loses its 800, which gives me after the third month 58,492.49. That's the nearest answer, $58,492. Now you'll notice they're going down each month. Each month that makes sense. In the first month, as I said, we had a gain of $300. Went up 300, down 800. Now in the second month, I haven't actually calculated how much interest we gain, but it's going to be less than 300. Okay, so we go up less than 300, but we still lose 800. We go up even less in the third month, less in the fourth month, even less in the fifth month, where eventually we're gaining very little interest, but still withdrawing that $800 each time. So it's not surprising that we'll start to see this drop off more quickly as the recurrence continues. The next part of the question, it would be tempting to go and do this without using a pattern, to essentially just find the three amounts of interest. If you'd like, you could do it this way. You could go 60,000 times 1.005. Then it was 59,500 times 1.005. Then it was 58,997.5 and multiply those by 1.005. And just add those three numbers together, which we can do. And that'll give me $892.49. Now, considering I earned 300 in the first month, and then a little bit less in the second, a little bit less again in the third, that kind of makes sense. If it had stayed constant, I would have earned $900 of interest. A little bit less than that makes sense. Now, for part C, by the way, I haven't found these values individually. I've just gone and added them up. What I've actually done is add these three numbers here together and then multiplied them by 1.005, just using a common interest factor there. You can do them individually and add them up. As I said, this one was 300. I haven't gone and done the other ones manually, but you can do it if you would like. They're a simple calculation. Now, we need to calculate the amount of money in the account immediately after the 94th withdrawal. This is going to need a pattern. So rather than doing my calculations here as I did in part A, I'm actually going to leave these in general terms. So A1 is my 60,000 multiplied by my interest factor minus 800. A2 is A1 multiplied by 1.005, losing my 800 again, which is 60,000 1.005 squared minus 800 times 1.005 minus another 800. Now this 800 here is this one here. This 800 is that one. Okay, that one was the first one, which is why it's got a 1.005 attached to it, because this 800 is built into there, into A1. Now, if I go A3, in fact, we can almost already see this pattern emerging here. If I write one more step for you, it's 60,000 times 1.005 to the N2 minus 800 outside of 1 plus 1.005. Now, if we go and do that for A94, that's what we're asked to do here, 60,000 times 1.005 to the 94, because I notice here, these powers are the same, whereas this power here is one less. But there are still two terms here. So when I go to add together the GP that is going to sit in those brackets, it's going to actually have the same power in the end, but it gets there a little bit differently. So it's minus 800, 1 plus 1.005 plus all the way up to 1.005 to the 93. Now, once again, as I said, there are 94 terms in there, or there are 94 lots of 800 that have been deducted, but the highest power is 93 because the first one is a 1. Now, if I do use my sum of GP formula, 60,000, 1.005 to the 94, that is just my compound interest minus 800 outside of, well, my first term in this GP is 1, so it's 1.005 to the 94 minus 1 over 1.005 minus 1. Calculate all that out and I get $187.85, and that's rounded to the nearest cent there. So I hope you can see that this is a typical type of annuity question, a occurrence relation question, where I've got my compound interest component. This is my compound interest, and this part here is my sum of a GP. All right, classic question here that through a lot of people was common to the standard paper in 2020 and probably caused a few more headaches there. It really does incorporate a lot of skills across the whole of the stats and correlation bivariate data topic, as well as including a little bit of parts of the other data topic as well. So I've got to write across 2 pages here, so I'm going to tear some things apart here first. All right, so we've got the mean temperature for this data set is 0.525 degrees Celsius below the median. So the median, Q2 here, is 22, which means my mean is going to be 22 minus 0.525, 21.475 degrees Celsius. All right, so that helps me out straight away. I've got my mean. Now, I've got also a total of 684 chirps was counted when collecting the 2 data points. This next piece of information here says that I've got 684 chirps that were counted across the 20 data points. So I've got 20 days, 684 chirps have occurred. So my mean for the chirps is going to be 684 divided by 20, which gives me 34.2 chirps per day as my mean, where this mean here was the mean temperature. Now, we've got this least squares regression equation as well that's partially completed. We haven't got the gradient there. We do have the y-intercept, but we do need to go find what that gradient's going to be. Now, what we're asked to actually do here, the other way we can represent this mean number of chirps here is y as my mean of the y values. Is to go and calculate the number of chirps expected in a 15-second interval when the temperature is 19 degrees Celsius. This piece of information here is what we're asked to do. Now, the only interesting thing here, this 15-second interval is kind of irrelevant because it's just saying we're measuring it over the same time period. So the 15 seconds can just be another number to throw in there. But we don't really need that at this stage. I've written down a couple of pieces of information that I know here. Now what I'm going to do is substitute these in. I'm going to substitute in my value for y, my mean value for y, 34.2 is equal to b, what we're trying to find, the gradient, multiplied by 21.475 minus 10.6063. Going to rearrange this so that b is the subject. Going to take 34.2 plus 10.6063, and I'm going to divide that by 21.475, and that's going to be my value for b, which comes out to be about 2.08644. We'll keep that exact answer in our calculator screen to substitute back in. So I've got y equals 2.08644 x minus 10.6063. Going to substitute in my value for x, which is 19. So I've got y equals 2.08644 multiplied by 19 minus 10.6063, which is approximately 29.03, or to round that to the nearest whole number, it's approximately 29 chirps. So we're expecting there to be about 29 chirps in this day. Now, there's a few parts to this question here. We needed to find we found this mean by subtracting from the median, knowing that our box and whisker plot tells us absolutely nothing about the mean of a set of scores. It only tells us about the mean, the quartiles, and the highest and lowest scores. We found this just using our mean calculation. That was a pretty standard calculation there. Then we substituted into our regression equation that we were given to find the value of B. Then we substitute in down here, we sub in our known X. Okay, to try to predict. By the way, this is a value we're trying to predict. So it is an approximation that we're doing based on our regression data here. But that's our loose steps there. Now that was worth 5 marks. Pretty big question to try to tackle. But again, it was really just a number of simple skills all really tied together. Normal distribution question here, where I've got 2 people who are chosen randomly, and I want to know whether they earn between $15 and $30. Well, $15 and $30 are kind of irrelevant until we take into account this 25 of the mean and 5 of the standard deviation. So what we need to see here is that this value of 15 is going to be a Z-score of 15 minus 25 over 5, which is minus 2, and our upper Z-score is 30 minus 25 over 5, which is 1. So what I really want to know here is what's my probability that I lie between a Z-score of minus 2 and plus 1. Well, if I consider this, I know that I've got 68% lying in here. I've also got 95% lying within 2 standard deviations. So if I use that 95 minus 68 over 2, which is 27 over 2 or 13.5%, that's going to tell me there's 13.5 in here, another 13.5 in here that I'm not interested in. So that means my probability is going to be 68 plus 13.5, about 81.5%. Now, that would probably get you 2 marks in this question, but I've got 2 adults here. Okay, probability that 2 adults are chosen at random. Find the probability that at least one of them earns between $15 and $30. I've got 4 scenarios here. I've got A and B. Both of them earn between that amount. I've got neither of them. And then I've got one of them does, one of them doesn't. Now, what I'm interested in is I can use this one and the or I can use 1 minus. The way I like to approach these type of questions is 1 minus P of none. Okay, now the probability that neither of these people is going to earn that amount is going to be the probability of neither of them earning that amount of money is going to be 18.5% squared. So as I come down here to the bottom of the page, my probability that at least one is going to be 1 minus 18.5% squared, which is 0.965775, or it's about 96, nearly 97%. I'm a very strong chance that at least one of these people earns between $15 and $30, or sits between a Z-score of minus 2 and plus 1. Part B here, the number of adults who work is equal to 3 times the number of adults who do not work. One adult is chosen at random. Find the probability that the chosen adult works and earns more than $25 per hour. All right, so this is again a probability question that's tied to a normal distribution question. So again, I've got 2 steps that I'm taking here, or really 2 questions I'm asking. So my first question is, I'm going to choose an adult at random, and really what this 3 times statement here means that my probability that out of a very large population of adults, the probability that someone works is 3 out of 4. The probability of no work is 1 out of 4. Okay. Now, we're going to do our first step here on our tree diagram. And the first step really is, the question is yes or no, work or no work. Okay. So if someone works, well, this is a 3 out of 4 chance, and this is a 1 out of 4 chance. If someone works, they meet our criteria. Find the probability that the chosen adult works. So they need to be along this pathway here. They need to work. And then $25 is our mean of our normal distribution. So they can be greater than 25 or less than 25. Okay, so I want this one here. I want to know if they're greater than 20. Well, because that's my mean, it's actually a 50% chance. Okay, so it's 50% chance, or 1 out of 2. We've gone with a fraction on the first one. Let's do a fraction on the second one. So 1 out of 2 and 1 out of 2. So that means that my probability that somebody works, yellow, and also earns more than $25 an hour, green, is going to be, my probability is 3 over 4 times 1 over 2, which is 3 over 8. Hope that makes sense, where we are tying these two things together, where the first one is, does someone work or not? They have a 3 out of 4 chance of working. And then if they do work, that's why we have no other information down here. Because if someone doesn't work, well, they can't be earning any money now, and they fail to meet our first criteria, which is that the chosen adult works and earns more than $25 per hour. So they've got to follow the top two branches. They can't go top, then bottom. They can't go bottom, then, well, there's no second step along that bottom one because someone doesn't work. A calculus question here involving logs in very general terms, just meaning we've got no numbers. We've got this equation, y equals c, the natural log of x, which means I'm going to differentiate that. That c is just a coefficient that hangs around the front, so it's just c times the derivative of log x, which is 1 on x, so that's c on x. Now, we've got some point p that we're talking about, so when I've got x equals p, we're going to have y equals c log p. I'm just going to substitute in my value for p here. Let's say p is some point up here. Well, that's the point p, c log p. And this is the equation of the tangent that I'm trying to find. Now, obviously, there's no numbers involved in this question other than the one, which is the y-intercept, which is just telling us this is a log curve that has not been shifted, translated left or right. But now I need to go find the equation of any line of this tangent, that blue line there. I'm going to need to do a point gradient formula, and I've got my x value, I've got my y value, I've got the basis for my gradient over here, but I need to actually get that in terms of this point here, p, or where x equals p. So my gradient is going to be c over p. Now, to go substitute into my point gradient formula, I'm going to have y minus my y value, c log p, equals my gradient, c over p, x minus p. Tidy that up a little bit, y minus c log p equals c over p x minus c. And so with y as the subject, y equals c over p x plus c log p minus c. They've got that written in slightly different order there in the solution, which you could go do if you'd like, but we're absolutely fine in having shown it that way. Part B asked me, find the value of c such that the tangent from A has a gradient of 1 and passes through the origin. All right, so we've got a couple of criteria here. What it means is my gradient's going to be 1, so I'm going to have my gradient equals 1, so therefore C over P, which is my gradient from here, is equal to 1. Or, to put it another way, C equals P. And also that if I've got a y-intercept of 0, it's got to pass through the origin. Okay, so that means that my y-intercept is going to be 0, which means C log P minus C equals 0. Now, as I look at this, I go, well, I've got C's and P's floating around everywhere. What I need to do is actually get an equation that just involves C or P. Now, I've got I can find either one of these, but what I'm asked to find is the value of C. So let's go and do that. Let's get it in terms of C, not in terms of P. So therefore, I'm going to take this statement here, that C is equal to P, and just substitute it into there. And I'm going to have C log C minus C equals 0, or say C outside of log C minus 1 equals 0. So what that means is that C is going to equal 0, which means P equals 0, which is a problem, because that would mean that my gradient, well, I do have C equals P, but it means I'm going to have a gradient that is 0 over 0, which is undefined. So what this means is this value here is just not going to produce a solution. Doesn't mean we just get rid of it, but we need to acknowledge that C cannot be equal to 0. It's in fact P that can't be equal to 0, but P is equal to C. So if I look at the next part here, that means I've got log C equals 1 coming from my my factor here. I'm going to rearrange that into exponential form, and I'm going to have, remember that's log base E, so I'm going to have E to the 1 equals C. Well, that means C equals E. That's my value there, or C is 2.71. We'll write it as C equals E though, not C equals 2.71. So C equals E, which means P also equals E. So my point would be EE, 2.71, 2.71, something like there. And that would mean it'd have a gradient of 1. And if we approximately sketch this, we'll see that it's right. It's going to have a gradient of 1, and it's going to pass through the origin. It looks something like that. Don't need to draw that sketch. I'd just like to know that what we've just found is in fact logical. Compound area question where we're going between two curves here. I've got a concave down parabola ax squared, a concave up parabola ax squared and a concave down parabola 4x minus x squared. We need to find where they intersect. So I'm going to say that ax squared is equal to 4x minus x squared. That's going to give me the points of intersection. It's going to give me 0, which I don't really need because we're only asked to find A. We know that that's the origin. That makes our life a lot easier. The second point, though, I'm going to find by saying I've got ax squared plus x squared minus 4x equals 0, which means I've got x squared a plus 1 minus 4x equals 0. Now I'm actually going to then take out a common factor of x. So it's going to be x outside of x a plus 1 minus 4 equals 0. Now, as I said, we get two solutions here. This is solution 1, x equals 0, but that's O, right? That's the origin, 0, 0. We don't need that one. What we do need, though, is this solution here, which I'm going to find by saying x a plus 1 minus 4 equals 0. Adding 4 to both sides, x a plus 1 equals 4, and x equals 4 over a plus 1 as we were asked to, which is exactly what we're asked to do. We don't need the y value there, I just need the x value, because when we come to part B here, we're going to find the value of A so that the area is a particular fixed value, and we don't need the y value to do that. I just know that it's less than 4, and the x value there is also less than 4. Let's go ahead and do part B now. All right, we had our curves here. The curves were y equals ax squared and y equals 4x minus x squared. We established that they met each other at x equals 0 and x equals 4 over a plus 1, where the a comes from this coefficient here of our first function, or our concave up parabola. And what we need to do is find the value of a so that I've got this area being 16 over 3 units squared. So I know that I've got these values. It's a plus 1, not x plus 1, sorry. 0. Now my upper function is my concave down parabola. So it's 4x minus x squared minus ax squared with respect to x. You can choose to factorize these together, or you can leave them separately. You can have an extra substitution to do if you don't factorize them. So I'm going to choose to factorize them. So I'm going to take out minus x squared, a plus 1, where a is a fixed value. So that is just a coefficient. A plus 1 is just a coefficient of x squared. I'm going to go ahead and do my integral here. So I'm going to have 2x squared minus x cubed on 3 multiplied by a plus 1 between 4 over a plus 1 and 0. Now I go ahead and do my substitution here. So I'm going to have 4 over a plus 1 all squared minus 4 over a plus 1 all cubed over 3 multiplied by a plus 1. And then that's all going to be minus 0. Now when I go and I'm going to write minus 0 there, because when I substitute 0 in for x here, I get 0. When I substitute x in here, I also get 0. I just get 0 times a plus 1. So I'm going to acknowledge that that is minus 0. So I'm not just doing the first factor. I'm just only writing it once. And then I've acknowledged it and I'm going to move on from it. So first of all, it's going to be 16 over a plus 1 all squared minus 64 over a plus 1 all cubed, and then I'm going to actually divide that by 3 as well. That 3 from the denominator there. That a plus 1 is dividing 4. The 3 is dividing the whole thing, so I can write it that way there. Then that's being multiplied by a plus 1. So what's actually going to happen here, that's going to become a squared, and that is going to go. I'm also going to be able to write 32 over a plus 1 all squared minus 64 on 3 a plus 1 all squared. Now I know that that is equal to 16 over 3. Okay, well, that's interesting. So now what I need to do is I need to try to put these two fractions together. They've already got a lot of the common factor that I need, a plus 1 all squared. Now I need to multiply this side by 3, which means this 32 is going to become 96. It's going to be 96, which is my 32 multiplied by 3. So I've got 92 minus 64 gives me 32. So what I've got is 32 on 3. A plus 1 all squared is equal to 16 on 3. The on 3's can actually go. Yeah, I'm actually going to reduce out these 16's as well, divide both sides by 16, and this will become a 2. So I've got, in the end, I've got something that looks like 2 over a plus 1 all squared is equal to 1. And that means that actually I can write that as a plus 1 all squared equals 2. A plus 1 all squared is equal to 2, which means a plus 1 is equal to root 2, and a is equal to root 2 minus 1. Now I haven't forgotten here that when I take this square root, I should actually have a plus minus there, but I know that a is greater than 0. Okay, so I know that a is positive, which is why I haven't taken the positive and the negative square root there. I have just taken the positive square root, because minus root 2 minus 1 is going to be like negative 2.41, whereas root 2 minus 1 is about 0.41. Okay, so that's going to be my value of A, so that I end up with that area being 16 on 3 square units. I've got an application to calculus question here. I've got a sine function, A sine pi on 26 t all plus B represents the population of mice for 0 to 52 years being 1 year. And we're told that it's a maximum here at 13 weeks and it's a minimum at 39 weeks. Or another way to put it, a quarter of the way through the year, that's a quarter of 52, that's 3/4 of 52. And I need to find these values of A and B. Well, A is all about my amplitude, and B is all about my midline, or the y-intercept here, because this is a sine function. So my midline. So I can actually do these two things together if you'd like. To find my midline, I'm going to take the average. It's going to be 35,000 plus 5,000 over 2, which is 20,000. What that means is that this value here is 20,000, 20K, which means I'm going to go 15 up to 35 and 15 down to 5. Now, once I've done that, that little calculation there, it also means I know my value for A, which is 15,000. Because A is my amplitude, how much higher and lower than the midline I go, and B is what's the midline that I keep coming back to here. So this midline that I keep coming back to, that we'll end up back with after 52 weeks, a whole year, when we're back at the same place we started, and after 26 weeks or 6 months, halfway through the year, we'll end up back at that 20,000 population again. For part B here, we're told or suggested to consider the graphs of MT and CT. Now, we were given the graph of MT. It looks something like this, where that was 52 weeks, that was 1 year, and where this was 20,000, going up as high as 35 and down as low as 5. And that was following our sine function, had a period of 52 weeks. Now we're asked to consider the graph of minus 80 cos pi on 26 t minus 10 plus 120. All right, so and then to consider where both populations are increasing. Well, to start with, I'm going to take my population of mice there. I'm going to say, well, the mice are increasing here and the mice are increasing here. And those values that we found, they were on our last graph, where this was 13 weeks, and we had 26 sitting in the middle, and that was 39. So that means our mice are increasing, MT is increasing, or M dash T is greater than 0, for T between 13 and 0, and also when T is between 52 and 39. Now, I haven't actually looked at the answer to this question here, but what I'm imagining is that the population of cats is also increasing at one of those 2 times, but probably not both of those 2 times. It'd be tempting to use some calculus here, but it will probably get very messy. But let's consider those graphs, just the graph of CT to start with. I'm going to use most of my space here to just draw that sketch. So as I start off, so first of all, I've got a midline of 120, which won't actually affect whether I'm increasing or decreasing. Now, my standard cosine function, it's got an amplitude of 80 here. I'm going to ignore that negative for a second. I will come back to it, which means I'm going to start at 200. And then our lowest value there will be 120 minus 80, which would be 40. So this is 120. In fact, my scale is quite off here. It'll get down as low as 40. I'll fix up that scale in a second. Now, what we need to think about is what this is going to look like. Now, as I said, I'm going to ignore the negative to start with. So if this were not a negative, if this were a positive cosine function, it would look something like this. It would start at 200 and it would go and make its full oscillation in the year once again, where that would be 52 weeks, because our period, our period is 2 pi over n, which is pi on 26, which is 52. Okay, so again, this is being used to model the whole year. But we've got two things that are changing this. First of all, it's a negative. So what it means is this whole thing is flipped. The whole function is flipped, so it looks something like that. Now where it finishes, where it starts at 40 and finishes at 40. Now the other thing we've got to consider here is that we've actually got a shift at the start as well, or a shift to the whole curve with this t minus 10. So what that means is when we start here, we actually are starting as if we were back here at minus 10. So it's almost like we're starting back here at minus 10. Okay, now the way that we can consider that is it's also we're going to finish as if we were at 42 weeks. Now it's not 42 weeks, it's at 52 weeks, but it's if we substitute 52 into here, what we get is 42. It's behaving like it's 42 weeks, even though it's 52 weeks. Now the question that we're asked here is where are both of these functions increasing? So we've got our values for MT. Now what we need to do here is for CT. Mislabeled that, sorry, that's CT, not MT. Now, where is this function here increasing? Well, this function here is increasing there. And that's the only section. Now, what we need to do is find what these turning points are. We could use calculus, but we're asked to consider the graphs here. Well, this was where I had my starting point before. It's no longer my starting point. It's actually 10 weeks in. That's 10. And the other thing we can look at here is to acknowledge that, well, this is still just a normal one full wave of a cosine function. I've possibly not drawn that quite low enough at the 52 weeks there. It could probably dip a little bit down, but it is just one full cosine wave that has been shifted, which means that it's going to be increasing for half the time and decreasing for half the time, which means this value here is half of 52, 26 plus 10, which is 36. So that means this one's going to be increasing between 36 and 10. So now we just need to find where these are overlapping. Well, it means that they're actually both only increasing over a very short window. If I have a look back up to here, where I originally said my red curve there, my very basic sine curve from part A was increasing between 0 and 13, first quarter, and the last quarter, 39 to 52. The only part where they actually overlap here is between 10 and 13. Because this whole, I'm not even going to try to put them on the same set of axes just because the scale is so far off in the first place, 20,000 as my midline versus 120 for the first and second functions respectively. But even if I draw these on a number line between 0 and 52, that's 0 and that's 52, my first one in black here is going to be between 0 and 13, the first quarter, and the last quarter. This next one in red here is going to be between there and about there. The only place where they overlap is that very small window there, which is between 10 and 13. So that's the only place where both functions are increasing. Very last part of our paper here, we expect it to be challenging. In fact, the whole of question 31 is quite challenging. It tests a bunch of different levels of understanding here for these last 5 marks and the previous ones in part A as well. But we're asked to find the rate of change of the mice population when the cat population reaches the maximum. Now, if you have drawn a very good graph here, you will know that this happens when t equals 36, and that is just from that graph above there where I can see it is at its maximum at 36 weeks. So what I know is that I've got t equals 36. So what I need to do is find m-t or dmt over dt, which is well, first of all, I'm going to rewrite. It's up the top there in blue. I've got mt equals 15,000 sine pi on 26t plus 20,000. The 20,000 is going to be gone straight away because it is a constant. Then I'm going to have 15,000 pi over 26. That's definitely going to simplify down, but I won't worry about that for now. Cosine pi on 26t. I'm going to substitute in 36, and what I'm going to get is 15,000 pi on 26, which can come down to 7,500 on 13. Doesn't simplify that much further. I've got an extra zero there, sorry. And that's cosine pi on 26 multiplied by 36. 36 on 26 is going to be 18 on 13. 18 pi on 13. Often these questions come out with a really beautiful answer. In this case, we don't get that. We just get this really weird negative number. But what it does mean is that at this point in time, at this 36 weeks, which on this graph in red at the top right, about there, we're definitely decreasing. The population of mice is decreasing at this time. And what we get is negative 642.7 and so on, which is about 643 decreasing. Okay, and that's mice per day, mice per week, sorry, because that's our rate in terms of time. We're losing about 643 mice per week at that point in time when the cats are at their maximum, which we would expect would be a time where just thinking logically about it, when there's more cats, there's going to be a bigger decrease in the mice population, which is, again, it's logical that makes sense.